Thanks for the introduction.
All right, you're very welcome.
Thank you for having me. It's nice to be back on college campus. Quick background on me. This is going to be a more nuts and bolts talk about data science. I unfortunately did not go to Cal. I went to the Cal of the East Coast, I guess, MIT. Did a PhD in computer science from there, and then have been, first it was called an algorithms engineer, then data scientist, now AI engineer. So been working as a data scientist for almost a decade now. And we founded Manifold with a couple of co-founders a couple of years ago. And really, who are we? We call ourselves an AI studio, really, using the buzzwords there. But we are a services company. We're a consulting company that helps companies with accelerating their machine learning and/or data engineering solutions. Most of our clients are typically non-tech companies, larger non-tech companies that are, taking their first journey into really becoming a more data-driven company, putting machine learning and data engineering as core assets to their business. And we're actually right down the street in Oakland, headquartered there, and also an office in Cambridge. A lot of alums stay there. So what is this talk going to be about? Really, it was kind of hard to fit everything into one talk, but what I want to do is just share some mental models for applying AI and make them real using some case studies from our work. So kind of at the top level, what we've, the main model, if you'll speak, so to speak, is we've adapted a lot of kind of techniques from CRISP-DM, if you're familiar with that, and human-centered design, made by IDEO. And we've come up with what we call our Lean AI playbook of how to go into a new company, a new situation where the business is trying to get value out of AI, and really making sure that we can deliver a win in 6 weeks, in 12 weeks, in 24 weeks, because that's really why they are hiring us. They want us to really accelerate getting value out of machine learning. And so I can't talk about all 6 of these steps, and I'll focus really mostly on understand here, which is understanding the business and understanding the data, a little bit on modeling, and then a little bit on user feedback. As machine learning people, data scientists people, we tend to focus a lot here on the modeling stage. In kind of 10 years of practice, this is really a very, very small piece of the much larger puzzle, the work that happens before and the work that happens afterward to really make the business get value out of machine learning. So talk a little bit about that. I'll jump right in. So understand. One of the mental models that we have is something I like to put LaTeX on slides because PhD habits die hard. I call it the AI uncertainty principle, which is really like the value that you get out of the AI is upper bounded by the business value of the problem that you're solving, the data quality that you have to solve that problem, and then lastly, the predictive signal. And again, as data scientists, we tend to focus a lot on, man, how good can I get the AUC? How good can I get the MAPE? But that is, in fact, the thing that you can't predict. You have to actually do the data science to do it. So really, it's very important early on in the project to focus over here up front, figuring out where to aim the AI and assessing how good the data quality is. And really, notice it's multiplicative. So if any one of these things goes to 0, the value over here goes to 0. And that's bad for us. It's bad for our clients. It's bad for a business. You don't want to get, it erodes trust. And you don't want to do that as a data scientist. So how do you prevent that from happening? What essentially is you have to do data understanding and business understanding. And the 2 techniques we use here are we do a business understanding workshop where we're really trying to surface, hey, get all the stakeholders in the room. This is usually CEOs, chief marketing officers, CTOs, potentially even finance people, analytics people, and really figuring out if we were to solve this problem better, what could the ROI be? And what often happens here is we will start an engagement being about, hey, we want to do preventative maintenance on these connected blenders that we have that makes milkshakes. Turns out that that was not the highest value place to focus the AI. It's better focused on, hey, can I instead forecast what flavors will be best to sell to each of these stores? That can lift revenue by 4 to 5%. That's a much better place to aim the AI and therefore get better ROI. On the other side, we're working with the tech team, the data analysts, the CTO, software engineers to figure out, hey, let's catalog your data sources. How clean is it? How rare is the event that you're trying to predict? Is it labeled well? Do we need to label more? Is the data joinable? In many of these large organizations, the data has been siloed in various different CRMs or data sources, and there's actually not even a join key. And so that is an issue that we face many times. Turns out you can use machine learning to learn a join key. I won't talk about that, but these are problems that you should be thinking about. So let's make it real. One of our customers was one of the leading registries in the United States, and their CEO wanted to hire us really to help serve her customers better. You know, I know that most of my revenues comes from a very small amount of my customers. How can I tailor my service to serve them better? How can I find these customers? And so what we went in there, we did the business workshop, we did a data audit, and we came up with a spec. And again, this was one of these stories where we went and they had a spreadsheet where you could track cohorts and whether they activated or not, whether they bought anything off the registry or not. And they kind of, the idea in their heads was like, okay, let's get to the next revision of this. And when we did really the business understanding, what we found out, what they really cared about was that they wanted to be much more data-driven in marketing and in product, but their biggest problem was that after people sign up, they didn't know whether they were going to be high LTV or not, a high lifetime value, valuable customer, until about 9 months later, their baby registry, right? So that turned out, after a lot of surfacing, was their biggest friction point in their organization. So how could you make this shorter? So then we did a data audit, and they had a lot of data they had been running the company for almost 10 years. So a lot of data, mobile app click streams, web click streams, marketing data from Facebook, Pinterest, all these things. They had data in their transactional database about how the customers were using the product, all the way to even demographics about their customers. They can join in from census data and other kind of creepy data sources where you can put in people's emails and it'll tell you demographics about them. So after cataloging everything, the spec that we came up with is we're going to build a model that will predict the final customer lifetime value after 9 months every day after sign up. So 1 day after sign up, 2 days after sign up, 4 days after sign up, 30 days after sign up. So every day we would make a new prediction of what the expected customer lifetime value would be. And in addition, we focused on only the transactional database because it turns out that the data quality was very high there. And there is a tax that you have to pay for every new data source that you bring online. And we thought, after looking at it, is that the transactional database, I think, has enough signal in and of itself. We don't need to pull in a terabyte of heap analytics logs or a terabyte of Mixpanel logs. We can just focus here on the transactional database. Another problem, I'm gonna use these 2 case studies throughout. So another client we had was an oil services company out of Oklahoma City, and their goal was to basically, again, be more data-driven about their maintenance operations. They have thousands of machines out in the field. They're breaking down. They actually don't sell the machines. They lease the machines, and they sell uptime. This is, again, out of the surfacing the business understanding. They sell uptime, and so they are also selling the maintenance contract along with it. And if the machine goes down, they lose money. In addition, they have to roll trucks to go do the maintenance on them. And so that was their burning problem. we also did a data audit. Turns out this was one of the cases where the data audit, they thought they had much better data than they really did. They had almost a decade's worth of service logs from the machines where the maintenance techs are typing in and clicking little check boxes about what parts they're using to fix these machines. They thought that they could use that to predict whether a part was going to fail. Turns out that this is what's very, very common in human input data. Humans are inconsistent over time and across humans. So there's a lot of inconsistency on how the exact same failure was written up and diagnosed and checkmarked in these service logs. In addition, the service logs had a very quickly changing lineage in the sense of how things were input 3 years ago is very different from things that are inputted a year ago, how they're input now. So the schema's changing and all this stuff is a very, very difficult data source to work with. Instead, what we chose to focus on is they also had a huge historical log of sensor data. They have 54 sensors on these machines collecting all sorts of things like vibration, temperature, the states of different registers on the gas compressor equipment. We chose to focus on that because machine data is much more trustworthy. The lineage didn't change as much because once it's out in the field, it's out in the field. And number three, it's just much more trustworthy. And so we ended up kind of focusing down on posing the machine learning problem is let us try to forecast if a major fault, and again, we have to define what a major fault is, and this is again where the business value meets the data, is we define major fault as whether the machine was down for more than 2 hours, because according to their maintenance organization, this is when they're getting many, many more calls. This is oftentimes when they have to roll a truck. This is often indicative of a true major failure in the parts, because otherwise these are kind of like computers too. It's like sometimes you can just reboot it and it comes back up and it's okay. But if it's down for 2 hours, typically we can't just knock it on the side and it'll be okay. There is actually something going on. So that's kind of the data understanding part. It's really, I just can't emphasize the importance enough. This is such an important part of doing data science out in the field, because if you don't aim it at the right place in a problem that is solvable with the data that you have, you will fail. Like, it's upper bounded by 0 and it's not going to be good for anybody and you'll spin your wheels. And so it's all about reducing waste that way. Let me move on. I think I'm not going to talk about engineering. I'm going to talk more about modeling here because it's kind of the fun stuff. But one mental model we also have, and this is actually by a friend of the firm. I don't know if you guys have seen this diagram, but this is by Monica Ragati. She's a data science celebrity of sorts, on the original LinkedIn data science team from about 10 years ago. But she has this fantastic diagram, which basically puts modeling right at the top. All the stuff we think is the sexy stuff is at the top. All the quote-unquote boring stuff is at the bottom, but the boring stuff is not actually that boring because it's the foundation. If you don't do this stuff right, you will never get success out of that. And so this is why engineering is really important. That being said, once you get to modeling, there is, I can't emphasize this enough either, and I'm sure you're being taught this in your courses, is build a baseline model, no exceptions. We'll hire new people out of school and they'll want to go be like, oh, we should use WaveNet and use this pre-trained model, we'll cut off these layers and we can put it in again, and it's just like, dude, let's try division. That's oftentimes how a lot of these initial conversations go. And division is a great algorithm, and it's been proven to work in a lot of places. So that's what I mean by a baseline model, right? Like, do the simple thing first. And rules of thumb that we found useful over the years is, if it's a regression problem, turn it into a classification problem, quantize. Even if you do multi-class. Because a classification is easier to understand than a regression. You can look at AUCs, you can look at class errors, you can learn from that. Secondly, usually the progression, I don't always start with just division. And like usually we're starting with random forests, then going to gradient boosted trees, then going to deep learning. Random forests, awesome. and oftentimes is just the thing that we put into production because it's just so easy to tune and it's so robust to overfitting. It's fantastic. And lastly, on the feature engineering side, pick a few features, iterate from there. And this is, again, a part of the engineering I didn't talk about. We're often working with the client and getting a list, a priority order list of what features that they think have the most predictive signal, and also scoring them against how difficult it would be to engineer them. You know, there's some things that are like a single SQL query. There's some things where I have to join across 17 tables and have like 24 subclauses in my SQL query. That's hard. Let's do the simple thing first. Or, you know, but maybe this thing has a lot of predictive signal. I do have to do that. So really judging that, and then iterating. Everybody here is very familiar with evaluation metrics. I like to classify them into two buckets. One bucket is the aggregate metrics. You know, this is the thing that you're actually seeing. How well is it performing? These are AUCs, ROCs, TPR at some false positive rate. But oftentimes we're looking, especially in the learning phase, is the individual metrics, so the sample level metrics. Here, this is a common plot that we look at. I'm looking at the, these are the true negatives and seeing what the model predicted on them. These are the true positives, and I'm seeing what the model predicted on them. And as you can see, some of the true positive is being really, really well. But many of them is not doing so well. So like, what's going on? Who are these guys where it's predicting so low? What's up with them? And we do kind of this analysis of, you know, just look at the four corners in the middle and let that guide you of what features you should make next, or perhaps how you should change the architecture. So making this real again, this is going back to the baby registry problem. We started with the two simplest features, which were what platform did they use to sign up? This is iOS or Android or, you know, Mac or Windows, and where they came from, Pinterest or Facebook. Just with that simple model and literally no features about the usage pattern. These are like super easy to make. I can just query it right out of the table. I got an AUC of 0.65. Then we added 11 more features that, you know, that was in our priority list. You know, write the SQL query, put it into the Python model. Got AUC of 0.90. So at that point, it's, you know, we're killing it. I don't, like, we had thoughts about maybe we should do embeddings and we should do like, you know, like a multi-scale convolutional neural network. Forget it. 0.90 AUC, this is amazing. 7 days after sign up, I can predict whether or not, this is actually like, this is a lifetime value bin of $500 or greater. I can predict that pretty accurately. So that's amazing. Let's move on to the next problem. That's a better use of a data scientist's time. Similarly, on the oil services problem, this was a much more difficult problem, like a huge data set, sensor time series. We had to sample it and kind of do some sample rebalancing because the things that we're looking for rare events. We did some feature engineering, went into the random forest, got, you know, with a few features, not so great in AUC, 0.65, added a few more features, got to an AUC of 0.78. This started to saturate a little bit. The custom feature engineering, we made like 5 or 6 more features, not doing great. We're like, okay, let's move on to convolutional neural networks. I think that could be really, really good. We did a multi-scale convolutional neural net where we look at a look-back window, similar to WaveNet, if you're familiar with it, to try to predict out 5 days whether a failure is going to happen. After 2 weeks of trying to tune the hyperparameters and tune the architecture, we weren't getting materially better performance. AUC is about the same. And so at that point, we went on to the next stage, and we were thinking about doing some more even advanced modeling, mixed effects modeling. We're like, you know what, forget it, diminishing returns. It's more important to move on in the cycle and put this in front of the user. So that's kind of the last step I'll talk about, user feedback. What do I mean by user feedback? This is literally, we are getting the predictions in front of the user that will actually use it. And so in this context, for the baby registry company, it was in front of the marketing team that was using this to make decisions on whether this campaign versus this campaign was doing better, in front of the product team. For the oil services organization, this was in front of the maintenance organization that is actually triaging these predictive maintenance things. we're doing working sessions with them. And again, this is more of a design philosophy, but it works really, really well in this space because you don't know how this is going to be used, and you don't know how well you have to do for the business to get value out of it. And so it's really important to get it in front of the user. And oftentimes, first we're going with nothing. We're just seeing what their flow is like right now. Then we go dump predictions into Excel, give it to them. Then perhaps we're making a Jupyter notebook where we can change a few parameters and playing with them there, well before eventually we'll build a web app or something like that around it. But this is very important. What happens is that, trust nobody, right? Like nobody trusts models, especially black box models. And even I don't trust black box models. Something comes out, you're like, it's probably wrong. That's like my first instinct from a model. Like, I'm an engineer by training, and it's magic that anything works at all. Because the shortcuts we're taking, right? But what we do is we'll do sensitivity analysis. And so we actually have a package that we use internally that we've developed that can probe the model in different ways to see if the intuitions that the customer has matches with what's coming out of the model. So for example, hey, is the predicted failure rate for the cohort match the historical average of failure with? If sensor A goes above this PSI, does the likelihood of failure go up? Because these are kind of known heuristics in people's heads. The model has to match that. Otherwise, your model is likely wrong. In addition, this is what builds trust in the model. The second thing we're often finding is that, this is not even we're finding, this is true. The predictions are never enough. The raw predictions are never enough. It's not solving the business problem. You have to build a UI around the AI. And so what do I mean by that? I'll make it concrete. So in the baby registry problem, the product team came back to us and they're like, okay, I want to change the product. I want to have this special promotion where if people do these 10 actions, they will get a free box that I will ship to them that's worth $25. And like, I want to know, will this make my LTV better? Is this trade-off worth it? I'm going to have a higher customer acquisition cost, but will the final LTV be worth it? How do I answer that question? This is the business problem that they care about. Turns out that the model can answer that, but just giving them raw predictions is not enough. We had to do a temporal A/B test where we actually like to come up with some new math to do that. How do you do A/B testing with predictions? And in addition, we had to retrain a model without the features that would be confounded by this experiment. And so in the end, we gave them a tool where you can take out certain features out of the model, retrain it, run it on 2 different cohorts. You pass in 2 different CSVs. It runs it on the 2 different cohorts, and it does the like this modified Welch's test to tell you, are the 2 predicted LTVs materially different from one another, and gives even a p-value. That's the thing that gave the product team value, not just the raw predictions. Similarly, on the other side, on the oil services problem, we delivered the raw predictions, and we were like really happy with ourselves in the sense of, hey, look, there's all these units that have high probability of failure today, and we were like thinking, oh man, they're gonna like roll trucks, and it's gonna save the day, it's gonna be fantastic. Turns out, we took the Excel spreadsheet to the maintenance people. They took a look at it, they double-clicked down into which units they were. Turns out that, oh yeah, those units, man, we're driving those way out of range. We know like that basin has really, really high line pressure. They break down all the time. We know that. We're driving it out of bounds. We're like, oh, okay. And so we're like, yeah, this means nothing to me because I know that I'm driving these machines in a place that will lead to more failure. So at least that was a sanity check on the model that is predicting that it's going to fail, but it doesn't have value. So what we ended up doing there to solve that first problem is we're looking at the differentials in probabilities. So the prediction comes out every day. We're really now alarming on when does the prediction change. So if it's 0.2 for a while and then it jumps up to 0.6, that is what we alarm on. Secondly, there is so many features to look at and so many sensors to look at, and there's so many different failure modes. They wanted better direction in their triage. We ended up implementing if you guys are not familiar with it, it's called the tree interpreter. It's a way that you can interpret what is coming out of a random forest or a gradient boosting tree, and it tells you why it's making the prediction. What features are driving the probability being high or the probability being low. That sort of explainable AI was very, very useful in the final web app that we delivered to this client because it helped them direct their triage. Otherwise, it was just taking too long to figure out what could potentially be wrong. What should I throw on the truck when I go out there? So, yeah, last slide. So, so that's it. I mean, there's many other things that I didn't talk about, like, use Docker, don't be a pirate, be the Navy, so be good about your software engineering practices, embed high cardinality, categorical variables. But really, hopefully I've been able to communicate a few of the mental models that I found useful. Any questions?
Also see that we're at 4:45, so I'm going to do the following. I'm going to take a couple of questions, and then we do have to move on from there. Will you be around after 5?
I will be around, yes.
All right, very good. So let's take a question there and then there.
Thank you, Sourav. I find this business case really compelling. I think you've probably run into a lot of interesting questions to answer every month. And I'm wondering, if we go back to the previous slide, I know modeling is kind of the top of the pyramid, but how much on this flow diagram, what percentage of time are you really spending with your clients in potential stages?
So yeah, like usually understanding that's up front, 1 week. Engineering is where we're spending a lot of time. We're like really understanding there's like tooling that we've built up for certain constants, like, hey, we're gonna deploy to the cloud, we're gonna share, we're gonna collaborate. But there's a lot of specifics of the problem that we need to understand, the scale, the velocity of the predictions that need to come out. So we're using different, we use stuff from the RISE lab and the AMP lab, Spark and Clipper and stuff like that. We're spending a lot of time here. This is also, we want to quickly get through the modeling phase to get something in front of user feedback. And then this is always unfortunate. There's a lot of time spent in deployment because it's the devil's in the details, deploying it to the cloud in the infrastructure. And then this is where we're not involved anymore, but we're monitoring this with the client. Right? So right now, that oil services company has been running validation for the past 2 quarters on the product that we've delivered to them.
Sir.
So yeah, thank you for the presentation. We talked during the break, so I was excited to see it. One of the questions that I had was, on the slide you had about building trust in your model. How do you avoid possibly goal seeking? So that's like having the answer that you're expecting to see, and then like working towards that. How do you avoid doing that?
So kind of like overfitting to expectations in some sense. That's a very, very good question. One that I haven't thought about too much. Usually these are basic heuristics that we're looking at. I don't think nothing has been so specific that antenna has gone off. I know this is probably an unsatisfying answer, but it's usually these heuristics are really reasonable ones that we're looking at. So if it was like some specific thing, it's like, oh, all these points have to match to one. Oh yeah, that has to be probability 0.71. It's never been that kind of an issue. These are much more global, aggregated sort of things that we're looking at.
Okay. Please join me in thanking Sourav. Thanks so much.
Thank you, everybody.